Under the stillness of the night sky, a silent watchdog named Tess orbits our Earth, peering into the far reaches of space. He was entrusted with a deep and pioneering mission. It looks for the shadows of worlds far from our planet, worlds that orbit stars unlike the Sun. Among the many observed stars, one that particularly caught Tess's eye was a red dwarf known as TOI 715, which hosts two planets, each of which could potentially reside outside our system. So, among the latest discoveries, we have two rocky terrestrial planets. One of them has already confirmed its existence. His partner, in turn, remains a candidate pending the final decision of further observations. So how did a satellite no bigger than a small bus orbiting our planet become the key to unlocking the mysteries of planetary systems many light-years away? What would it take to discover the existence of distant worlds a million miles away? In 2018, the Silence of Space TESS, the Exoplanet Survey satellite, has been launched on a monumental journey. The mission was designed to uncover the mysteries of the interstellar orbits of distant worlds far from our system. Armed with sophisticated instruments, TESS stands on the watch, constantly observing some space. TESS's innovative design incorporates the latest in space technology at the time and includes wide-angle cameras that provide an unprecedented panorama of the sky. The array is carefully calibrated to detect minute changes in starlight, a sign that a planet is passing in front of its host star. This precision allowed TESS to examine more than 200,000 stars during its 2-year primary mission, with each observation potentially holding the key to discovering a new world. However, TESS carries not only its own story, but also Kepler's predecessor in the search for exoplanets. Although Kepler's eye was focused on the smaller field of stars, his explorations were also fruitful, discovering thousands of new worlds and painting a galaxy full of planets. TESS builds on this legacy, casting a wider net across all sky surveys and bringing us closer to the dream of finding another Earth. Together, TESS and Kepler have transformed our understanding of the cosmos, turning the once beautiful version of the universe into a clear reality. The telescope's planned 2-year primary mission has been extended, illuminating the path to understanding our place in the universe until now. The observatory's monumental work revealed more than 7,000 candidate exoplanets earlier this year. This remarkable achievement emphasizes the abundance of planets outside our solar system. The task of compiling a catalog of these celestial bodies is no small task. It begins with a careful observation of the stars in search of the characteristics of the companion planets. The criteria for an object to be considered a candidate are very strict. They require clear evidence of consistent orbital patterns, size, and mass estimates indicating the presence of a solid or gaseous body, and most importantly, the possibility that the planet is in the star's habitable zone. At the heart of our search for Earth-like worlds is the concept of a habitable zone known as the Goldilocks zone. This is a notional cluster around a star where conditions may be optimal, neither too hot nor too cold, for liquid water on the planet's surface, an essential component of life as we know it. Historically, space giants, large planets with dense gaseous atmospheres, have dominated our catalog of discoveries. Their size and proximity to their host stars makes them more visible to our observing instruments, casting long shadows and appearing brighter than starlight. A major area of exoplanet research is the discovery of small Earth-like planets. These rocky worlds, like our Earth, present a more difficult problem. Their subtle signal is often lost in interstellar explosions. Astronomers have many methods to detect the abundance of such worlds, from astrometry to gravitational microlensing. About 50 planets have been discovered using the pulsar. However, we won't go into each of them today, that's a topic for another video. But let's start with the basics to make sure we're all on the same page and briefly review the trio of complex methods, as good as the others. These methods, direct imaging, radial velocity method, and transit method, form the basis of our sky search. Direct imaging captures photons originating from planets billions of kilometers away. To date, more than 230 confirmed exoplanets have been discovered using this method. This method, similar to photography, is most effective for large planets at significant distances from stars, where the star's brightness cannot block the planet's faint light. Next, we dive into the radial velocity field, which allows us to read the celestial interactions between stars and their planetary companions. As the planets orbit, they create a gravitational pull, causing their stars to wobble slightly. This wobble affects the color of the star's light, shifting it toward the red or blue part of the spectrum. More than 1,000 planets have been confirmed through careful measurements of this phenomenon. However, it is the transit method that has revolutionized our sense of space, especially with missions like TESS and Kepler. This method allows us to observe the occasional dimming of a star, momentarily blocking its light when a planet moves in front of it. The depth of this obscurity allows us to determine the size of the planet and the regularity of its transits and its orbital period. TESS and Kepler used the power of the transit method to spectacular effect, examining thousands of stars in search of signs of planetary transits. With TESS's wide-angle cameras scanning large areas of the sky and Kepler's precise focus on star fields, these observatories have catalogued countless new worlds. The beauty of the transit method is its simplicity, and the wealth of information provided, from planetary sizes and orbits to potential atmospheres, when combined with other methods. Finding Earth-like planets in their stars' habitable zones is as difficult as watching a star fly past a lighthouse a few miles away. These terrestrial worlds, smaller and darker, are often obscured by the glare of their brightest stars, making their detection an unusually delicate and precise task. Gravity is a large mismatch between an Earth-sized planet and its star in size and luminosity. When such a planet passes in front of a star, it blocks only a minuscule fraction of the star's light, resulting in so little light that it tests the limits of our most advanced observational technologies. However, as we search for this world, M-type dwarf stars become beacons of hope. These stars, smaller and cooler than our Sun, offer unique advantages for finding Earth-like exoplanets. The waning brightness and size of M dervishes means that the planets orbiting them can make specific transits, making it possible to identify them. In addition, the habitable zone around these stars is much closer than that of stars like our Sun, resulting in shorter orbital periods for habitable planets. This proximity not only leads to more frequent transits, but also increases the chance of capturing these events, thereby increasing the chances of finding habitable worlds. Let's move on to Dransfield and his team's recent discovery, which has sparked a lot of interest in the astronomy community. As a result of their intensive search, they found not one but two terrestrial planets orbiting a red dwarf known as TOI 715. Now, TOI 715b is the first of these two planets to be confirmed, and its existence is on the discovery list. With a radius 1.5 times that of Earth, this world orbits its star every 19 days and has an equatorial temperature of 234 Kelvin or -38 Fahrenheit. It's a cold area, but at the same time it's a very potential habitat if there's an atmosphere capable of trapping heat. TOI 715b's journey from a simple candidate to a confirmed exoplanet began with a test transit method. As the planet passed in front of him, he noticed that the star had dimmed slightly. This initial detection was supported by several observations involving ground-based photometry, high-resolution imaging, and statistical analysis by facilities such as the Los Cumbres Observatory, Global Telescope Network, and the Extra facility. His partner, with a more robust name, remains a candidate. We look forward to the next review. If confirmed, it would be the smallest exoplanet detected by TESS in the habitable zone. The planet's estimated temperature is 215 Kelvin, a very cold -72 Fahrenheit. It is 6% the size of our Earth and makes a complete revolution every 25 days. This orbital period indicates that it is at the outer edge of its habitable zone. The 4-3 coincidence of the orbital period with TOI 715b gives the system interesting dynamics, suggesting a potential orbital resonance. Such resonances affect the long-term stability and evolution of planetary orbits. In resonant systems, gravitational interactions can cause changes in the eccentricity and inclination of the orbit over time, stabilizing the orbit without causing close encounters. The study suggests that confirming the companion candidate and its precise orbit can provide valuable information about the system's mass and dynamical state, allowing for detailed characterization of dynamical systems in the future. Wave power plays an important role in shaping the orbits and rotational states of planets and resonant systems. These forces can lead to ocean warming, affecting geological activity, and the thermal distribution of planets, which in turn can affect their habitability. Understanding these dynamics is critical to achieving long-term planetary stability and habitability. As we said, the search for habitable worlds is not just about finding planets in the habitable zone. A planet's atmosphere, composition, and geological activity play a major role in determining its habitability. For example, a dense atmosphere can trap heat, expanding the habitable zone, while a thin atmosphere can do the opposite. However, the enigmatic nature of planets orbiting M-belt stars, with their erratic flares and radiative emissions, presents a paradox in the search for habitability. These stars, often with interstellar activity, have the ability to strip the atmospheres of those planets. The authors of the study note that although stellar explosions can provide the energy needed to catalyze biological processes, they can also pose a significant threat to the atmosphere and position of protective magnetic fields. But in such murky conditions, the James Webb Space Telescope is ready to use its suite of advanced instruments and shed light on the composition of the planet's atmosphere. JWST uses transmission spectroscopy to capture the faint signals of starlight passing through the planet's atmosphere. This method allows us to decipher with relative precision the components of the atmosphere, from water vapor to methane, each leaving a unique spectral fingerprint. While in orbit, Webb's schedule of scheduled observations is very tight, but our team of scientists on Earth wasted no time and calculated spectroscopy metrics, or TSM for short, for these planets. TSM plays an important role in evaluating the prospect of exoplanets for studying atmospheres using TSM spectroscopy. TSM, developed by Kempton and his team in 2018, is a standardized tool for comparing the potential of different exoplanets to reveal atmospheric properties using this method. For TOI 715b, TSM calculations were made under different assumptions about the planet's composition, rocky world, and water world. These calculations take into account the size of the planet, which is slightly larger than the threshold normally used to define terrestrial planets. As a result, different scaling factors were used to ensure a fair comparison with other known exoplanets. The results show that the planet, especially in the water world scenario, may show a transmission signal similar to the well-studied mini-Neptune LHS 1140b in the constellation Tethys, given the detected atmospheric properties. However, in the extreme scenario, the TOM 715b TSM is below the recommended threshold for terrestrial vegetation observations, and more than one JWST transit may be required to detect atmospheric significance. The study authors suggest that molecules such as water, vapor, and carbon dioxide play an important role in maintaining surface temperatures suitable for liquid water. Having an atmosphere with these greenhouse gases can expand the habitable zone and improving life chances. The position of planets in the conservative habitable zone, as well as their potential composition, naturally raises questions about their habitability and the initial processes that could lead to the precursor molecules of life from inorganic compounds. Meanwhile, we look forward to JWST finally setting eyes on this system, not only because of the scientific debate about the possibility of planets orbiting M-jackets and the effects of stellar radiation, but also because of the perspective. Promise. Not just answers, but a perspective that promises a new understanding of the nature of life in the universe. For decades, all of humanity has been asking the most important questions for the entire universe. Are we alone? Today we will tackle the Fermi paradox by approaching the most anticipated answer through artificial intelligence. Through millions of images and hundreds of hours of observations of the universe, AI has already been able to detect radio signals from extraterrestrials, revealing which planets are inhabited by a surprising hypothesis about the history of life on Earth. Now, you'll learn how AI is cracking the mystery of extraterrestrial life and whether we really are the first civilization on Earth. It's no secret that the Drake equation has traditionally been used to search for extraterrestrial life. In general, the formula consists of 7 factors, which are based on clear and simple logic, taking into account the rate of formation of planetary systems conducive to the development of intelligent life, the proportion of such systems in the Milky Way, and the average duration of civilization. Can be used to estimate the number of cultures likely to exist in the galaxy today. So the simplicity of this formula, if all the members are present, can give us a one-time answer as to whether we are alone or not. But here comes a serious difficulty. The main shortcoming of the formula is that it currently lacks all of its components, except for the first, the conditional star formation rate for the development of life, R. In particular, the value of the culture lifetime L cannot be calculated due to the heterogeneity of the foreign order. Therefore, this factor remains speculative. In the presence of these shortcomings, the creation of a theoretical number for the approximate number of extraterrestrial civilizations must be postponed for a long time. But what if there was a way out? Some important values of the FCFIFL equation can be determined by including L without leaving the planet. The process of creation of life is incredibly complex. Many conditions must be met for the development of an intelligent civilization such as ours, such as abundant water, heat, seasonal changes in climate, abundant chemical elements for building and nutrition, and so on. Therefore, it is very difficult to search for extraterrestrial life. At least one of the conditions is not suitable, and a planet can be included in the list of people where living organisms will never appear. Also, life on Earth could have gone through several stages before reaching its current level. In other words, intelligent life could have existed long before humans became extinct under certain climatic conditions. In 2018, 2 astrophysicists, Adam Frank and Gavin Schmidt, used the planet's geological history to investigate whether industrial civilization could be discovered. That is, if there was a culture that developed during the time of the dinosaurs hundreds of millions of years ago, is there any evidence of its existence? We are not talking about buildings and statues. They will not remain after a few million years, but about chemical traces such as carbon sequestration, plastics, radioactive elements, or climatic and ecosystem changes. This thought experiment is called the Silurian hypothesis, based on the eponymous intelligent species that created civilization before humans in the Doctor Who series. This hypothesis not only overturns the entire history of our planet and calls into question the conditions for the development of life, it also leads us to an approximate solution to the Drake equation. For example, looking at extraterrestrial civilizations from the perspective of their impact on the planet could change the way future planetary research is done by showing scientists what to look for. According to NASA, we currently know of 9,820 exoplanets that are candidates to support life. Observations on these planets of nitrogen dioxide or chlorofluorocarbons as products of industrial processes may indicate the presence of an advanced civilization in the past. The best part is that we can find this trace now, because this compound can be detected by observing the light falling on distant exoplanets, along with various combinations of methane and oxygen in the atmosphere, indicating the presence of simple life. Traces associated with technological progress are called techno-signatures of civilization. Unlike various biosignatures that do not guarantee the presence of life, techno-signatures cannot be confused with natural processes. Thus, focusing the attention of scientists on them can reveal to us the hidden world of alien civilizations much faster and more accurately. Generally, scientists look for technosignatures that match our technological footprint in outer space. However, according to Adam Frank, aliens are not magical because their hypothetical civilizations and scientific discoveries are based on chemical and physical principles known to us. For example, in the 1960s, SETI scientists came up with the idea of looking for unnatural radio signals in addition to the usual biosignatures and pollutants. Remains the most common type of quest, and communication with unknown civilizations still fails. However, this method has several serious problems, the most important of which are radio signals that can be reflected from space objects and attempts to locate us by mistake. But at this stage of our progress, in addition to radio signals, we can detect industrial gases in the atmosphere, unusual heat patterns, and polluting particles as high-energy neutrinos. But the gases in the atmosphere can be the product of strange geological activity on the planet, such as Neptune's moon, industrial propane gas in Triton's atmosphere, you may know, and possible traces of life. Channel. However, high-energy neutrinos have unusual traces. Although ordinary neutrinos are the most abundant particles in the universe, high-energy neutrinos, which could hypothetically increase the energy of ordinary neutrinos by 1 billion times, can only come from accelerators of Planckian particles on such a small scale that they do not yet exist. Humanity. The discovery of such neutrinos would represent a major advance for an alien civilization, as such a collider would need an energy density that would allow it to withstand very intense electromagnetic fields, and such a location is only near a black hole. More visible traces of a highly developed culture in space are astrophysical structures, and transport they are not easy to find. The most famous megastructure is the Dyson Sphere, a hypothetical technology that orbits a star and uses its energy to meet the energy needs of extraterrestrial life. If such a structure were located thousands of light years from Earth, scientists could observe it by observing an eclipse of a globular star. However, Dyson's region can easily be confused with the natural appearance of older stars. It can also be difficult to detect spaceships and zones with motion or strange signals, as they can also be confused with ordinary space objects. For example, the very strange nebula star Oumuamua, discovered in 2017, caused a lot of controversy in the astronomical community because it did not show any signs of moon or asteroid activity. There was a version that Oumuamua was an outer zone, but it was still classified as a comet. Therefore, searching for technosignatures is a complex task that requires years of analysis, observation, and modeling to approximate what we see. But our growth is also rapid and unstoppable. In the near future, searching for signs of life on thousands of planets will become commonplace. Artificial intelligence will help us to achieve new progress. Recently, AI has begun to gain popularity both among ordinary users and in scientific circles. Astronomical research requires dozens of hours of detailed analysis and comparison with previous results, even for a single object. The amount of data to observe 820 stars is 150 terabytes, or 480 hours. With machine learning, this demanding process can be significantly accelerated, and according to University of Toronto researcher Peter Ma, combined with the next generation of telescopes, AI will help study and observe not just hundreds but millions of stars. The benefits of AI's rapid processing of large amounts of data are expanding the search for extraterrestrial life. In 2023, an artificial algorithm led by Peter Ma analyzed 480 hours of data from the Green Bank Telescope in West Virginia and found more than 20,500 signals that resembled technological signals. From this number, the scientists selected 8 signals, technosignatures, and the rest of the array consisted of underground radio signals. Despite having to manually select the signals, the scientists did not have to spend nearly a month to evaluate what the telescope recorded. Despite the interesting findings, repeated listening to the signals was inconclusive. Nevertheless, even this initial success shows that AI can be used to collect data, and in the future, after various trainings, can produce meaningful results. The biggest challenge for SETI is actually not so much data, but the difficulty of distinguishing between human and extraterrestrial signals. Although the first model developed by the scientists made potential discoveries, it could not distinguish technological signals. Scientists are now planning to use this AI model to analyze data from telescopes and archives. In addition to looking for radio signals from intelligent life, AI can also look for biosignals and model their patterns to infer that there is life on the planet. Recently, scientists at the University of Oxford, led by Dr. Kimberly Warren Rhodes, trained an AI algorithm to classify biosignatures using aerial images of the Atacama and Altiplano deserts in South America. Ultimately, the model was able to identify the biosignature in 87.5% of cases. One of the participants in the study, PhD of Computer Science, Freddie Kalaitis, believes that further testing and machine learning will be crucial to the future search for signs of life and to build useful routes for exploring Earth analogs, especially Mars, as well as Mars. Interesting months, etc. It is the gas giants of the solar system, Europa, Enceladus, and Titan. In addition, researchers hope that AI will be able to analyze the mechanisms of life development in planetary systems, such as eternal cold, extreme conditions, given the abundance of known data on such planets. In particular, AI can help with the less exciting but necessary work of advancing what we know about space. AI can systematize all the knowledge gained from observing thousands of space objects. AI can examine several factors about an object at the same time, such as its surface composition, terrain features, and other factors that affect the focus of the analysis, giving scientists a complete picture of the object of study, which will take months of work. AI's shortcomings are rapidly diminishing with constant and varied training, clearly showing its great potential to explore the entire visible universe in detail, and more importantly, to increase the chances of finding extraterrestrial life. But it also has its downsides. AI always responds. As strange as it sounds, AI is much faster than humans at seeing patterns and analyzing large amounts of data. Without a specific understanding and behavior of human activity, and based on its training material, the algorithm can provide answers that astronomers do not understand and cannot see a possible error. For example, astronomer Ingo Waldman taught an AI called Robert to distinguish water from other planets' atmospheres. But Robert did not understand what caused the change in molecular composition and shape of water. So AI needs to be fine-tuned, but its time will come. AI also won't be able to confirm traces of extraterrestrial life, as the search for technological signatures can be simplified by the ability to analyze databases through the planet's known history, making it a little easier for machine learning to find signs, a pre-human civilization. Hypothetically, it existed on Earth hundreds of millions of years ago. Let us return to the Silurian theory. Although it does not yet provide a rough idea of how pre-human society developed, we can make some guesses. For example, a certain type of intelligent mammal could have appeared 60 million years ago. His civilization only lasted 100,000 years and was destroyed by some cataclysmic event, returning intelligent life to its embryonic stage. But no evidence can be given for this idea. For an undeveloped civilization like ours, millions of years is absolute oblivion. Even if they were fossils from that period, they could have changed dramatically due to environmental influences. Thus, according to Solaria's hypothesis, we can find evidence of ancient civilizations based on human remains. AI can help with this. Machine learning will be able to distinguish small accumulations of industrial waste better than humans, while modeling the way these ancient elements spread. 56 million years ago, Earth experienced what is known as the Paleocene-Eocene thermal maximum, which caused global temperatures to rise by 15 degrees Fahrenheit, reaching temperatures of 70 degrees Fahrenheit at the poles. Scientists also noticed an increase in the ratio of carbon to oxygen in the atmosphere during this period. Perhaps one of the reasons for this was the industrial age of the previous civilization. On the other hand, emissions may be the result of temporal changes in the temperature background. According to Adam Frank, The RETM has not experienced dramatic changes in atmospheric composition through carbon emissions compared to the modern industrial era, so it may be due in part to natural processes. However, such activities of the previous civilization may have been short-lived. That is, its influence on the Earth was there, but due to its insignificance it will not be easy to prove it. On the other hand, a hypothetical pre-human culture left no traces of pollution such as fossil fuels or plastics, according to research led by Frank and Smith at the University of Rochester. Although such techno-signatures are not known to be widespread, at least the fuel footprint for a civilization with a hypothetical long history is likely to be significant. This fact raises doubts about the validity of the hypothesis of leading scientists. However, absence of evidence is not evidence, says University of Pennsylvania astronomer Jason Wright.